Broadcore is a modular construction system that is lightweight, strong, easy to ship and assemble. The properties of the Broadcore system enable a fully new approach to construction. The Avabot system is a vision of how robots will someday be building the cities of the future. The system contains 6 components that interweave robotics, artificial intelligence, virtual reality and education. The first part of the system is the virtualization of the real world. We can use satellite data, cameras and distance sensors on drones and robots, existing 3D models and other sensors to capture a virtual model of the real world. For example, we have a construction site. By using GPS data, drone scans and traditional architectural measurement tools, a map of the construction site and its environment can be created. This map can then be used to create an exact VR simulation of the construction site and its surroundings. After the digitalization is completed, the next component of the system, the actual VR platform, is used to create the architectural designs. In the VR platform, global teams can collaborate together in real time. They can use Broadcore Lego-like tools to compose and conceptualize building in the VR simulation of the construction site. The VR platform can also access project management system for web interfaces and thus can also be used for team meetings and project planning. After designs have been completed, the next component of the platform covers the client approvals, payment and marketing. Clients can experience a full-scale and interactive presentation of the building designs in virtual reality. After the client approves the designs, inbuilt blockchain technology can be used to approve smart contracts and receive payments. The created designs can be used for further marketing by giving new potential clients and a greater public and immersive virtual experience. When the designs have been approved and payments received, the parts of the buildings need to be manufactured, which brings us to the next component of the system: smart factory automatization and manufacturing. As the robots are connected to the VR platform, they can access the virtual designs and automatically manufacture the parts that are needed for the building. On top of that, we can use VR to enhance and create new factory processes. A virtual simulation of a factory and multiple robots like CNC machines, laser cutters, 3D printers and assembly lines can be created by virtualizing the factory environment. In a virtual environment, multiple robots can be simulated and trained by using AI. They can learn how to collaborate and improve the manufacturing process by using deep learning and reinforcement learning techniques. Because the process runs in virtual reality, it is much cheaper and safer than trying to train the real robots. After the virtual training is completed, the AI models can be transferred onto the real robots, so the robots can use the newly acquired skills in the real world. The system can also be used to reduce the robot development cost of new robots by building and simulating a new robot in a virtual world instead of prototyping in the real world. Humans can remotely operate robots through VR. By doing this, the robots can learn new skills from human operators by creating training data for AI. Piloting a robot from VR is a very safe way of operating large machinery. A human can look through the eyes of the robot and remotely pilot and operate the robot. You can use the robot to execute a complex task that would be hard to program with traditional methods. The task execution can be recorded and used to create training data for artificial intelligence. When enough training data is collected, the robot can learn from the data how to execute the task without the help of a human. After the parts are manufactured, they need to be delivered and turned into a building. The vision of the system is that the robots autonomously handle the packaging and shipping of the parts. As the robots can access the virtual building plans, they will also be able to assemble the buildings without human help. The last component of the system is its use in education and training. Through gamification of creative and technical processes, Young students and employees can experience fun and engaging trainings. When combining the gamification with the immersive nature of virtual reality, this will create a more exciting and engaging learning experience of architecture, design and engineering than common learning approaches.
Hi, I'm Mark.
And hi, I'm Sebastian. And this is
Avabot.
Hi, I'm Zach. I'm developing the virtual reality platform and tools.
So what is the Avabot? The Avabot is a teleoperating system, or also called in robotics a telerobotic system. So that means you can remote control the robot. You can be in another place of the world and control the robot, and basically look through the eyes of the robot to control the robot. So the components of the Avabot are a touchscreen that lets you control the robot without any computer or anything else. So you just connect the Avabot, plug in the touchscreen, it automatically loads up the user interface and you can control the robot. We have the robotic head, which houses the brain, the electronics and the camera that we can move. And we also have a robotic arm, so this is a 6-axis servo motor arm, which we can control with the user application. So now what I'm going to do is I'm just going to activate the arm. So when the application starts up, the application asks you to turn on the motor controls. So let's do that. Let's activate the motor controls. Awesome. And activate the motor controls. Now we will see in a second that the arm just will start up. Awesome. There we go. Now I can close the menu. I can also use the menu together with a mouse, if a mouse is connected to the robot. So now I will show you the camera. So now we are looking through the eyes of the robot. And I can move the camera of the robot. Hey, that's me. There's Mark, he's filming.
Hi.
There's the robotic arm. And we can also control the camera by just clicking on the camera feed and moving the camera around. And we can see the size of the robot. The next thing, the next UI screen is the actual control section of the robot arm, which is this one. So we have a controller for each motor in the arm. Here we can control the clamp, the elbow, we can rotate the elbow, tilt it down, and these are for the other motor controls. So let's tilt down the elbow. Oh, it's the wrong direction. So, and now we're just gonna pick up that pen. Rotate the platform. And open the clamp. And there we go. then, so these are the basic controls of the robot. And as mentioned, it's a teleoperating system. So this touchscreen is directly connected to the arm, to the robot head. But I have my computer here now, which is only plugged into the power, and the computer connects to the Wi-Fi router, and the robot is also connected to the same local Wi-Fi. So within my computer, I just have a browser that's running. So all I need to do is to go to avabot.local. If you are on a Windows system, you just go to http Avabot, and I have a control screen of the robot. So now I can go to the camera control as well, and I can control the robot over Wi-Fi. Hey. Same thing with the arm. Can go back and control the arm of the robot. And the system is built in a way where the two user interfaces are different, and I can actually control how much access I want to give to someone that's operating the robot. So one example is like I'm working on the physical arm and doing some repairs. I wouldn't want somebody to be able to start and stop the arm. So what you can see here, you can deactivate the arm, you can exit the UI, you can shut down the system. But if we look over on my network controlled robot, I have a different UI, so I actually can't shut down the system, I can't shut down the arm. But what I can do on the system is I can go to network options, and then there's an option called network control. If I click this option and I enable full network control, now the full network control is enabled. If I now go back to the to my network controlled robot, oh, I have the full UI. And what I can do now is I can just deactivate the robot over the network. Okay, click deactivate. And the robot arm is shut down. And I can activate it again. Activate motor controls. And the robot will start up again in a second. And one last feature is internet access. So at the moment the access of the robot is limited to our local network. So what I can do now is I can go to this page, broadcore.pagekite.com, and it will say, okay, the service is temporarily unavailable. Now going to the robot control, I enable the internet access, go over to this page and go back to broadcore.pagekite.me, and now I'm actually accessing the robot through the internet. So this is now, I could be in another part of the world, I could be in Europe, in China, in the US, and actually control the robot through the internet. So I will show you the arm control. So it takes a little bit longer to load up because it needs to go to a server that sits somewhere in the world. And let's control the arm. Fast. And to see, so we can see actually the actual robot control is quite fast. But now if I look at the camera stream, we will see there's quite some delay. So the picture is getting stuck, I'm winking, and because it needs to buffer the video stream. And we will be able to improve that in the future by working on the networking architecture, doing video compression. So that's still something that we will be able to improve in the future. So now the video is catching up. There's like a couple of seconds of delay. And I could also move the camera. And yeah, it will take a couple of seconds for the system to catch up. And that's basically it. So now to turn off the robot, we can just click on the shutdown option. It will ask, okay, should we turn it off? Yes, we turn it off. What is going to happen is the robot arm will go back into its rest position and the system is going to shut down. We'll also use the internet connection. That's Avabot. And here we can see how we can operate the robot from virtual reality. On the right side we can see the user interface in VR, and on the left side the real robot.
Hello, this is your tutorial for the Avabot system. So your grip buttons on your controllers are how you activate the movement mode. The right hand will move you forward, the left hand will move you backwards, and if you press both, you'll go faster forwards. Then on your controllers, these are your radial menus. You can use your thumb pad to access these. Over here you have resizing and movement modes. Then on this hand you have the camera, prefab placer, painting tool, prefab eraser. So let's go ahead and fly over here. So to use one of these radial menu buttons, you simply move your thumb pad over it and then push the thumb pad in. And so now here I could grab and climb. So this changes your movement mode. And then to go back, you press the button either on a Vive just above the thumb pad or on the Oculus directly to the side of the thumb pad. All right, and now I'll show you the main tool on this version. It's the prefab placer. So once you click it, you can open it up and here's your palette. On the left side are all your different palettes. So these are sort of the core building block Legos. The bottom one has some trees and foliage. And then the middle one is an entire pre-made floor. Then this button up here minimizes or expands your palette. So once you click one of the slabs, you then now have some new buttons available. On your right hand, you can move your cursor in or out. The grid items don't scale. The trees and the organic items will scale. And then on your left hand, you can rotate it. And then you can also undo. Like once you place one, you can undo your last placed object. So that's kind of the core of the prefab tool. It's nice to minimize this to get out of the way once you select a brush. Once you create some objects, you can go into your walking movement mode and it will ground you to the surface so you can walk around your buildings that you've created. Add some nice nature. Once you create some planters. The painting tool is just to like make little markings to share information or ideas with other people on your team. The camera, right now we have takes a second to load it, but you can see this is a little stills camera to generate content to then export and share. Okay, let's go ahead and fly over here to the control panel. We want to make ourselves large because this panel is pretty big. So there's some buttons. You can use these to change these panels. Over here we have a nice little YouTube panel with some broadcore content. And over here is the art of Avabot. Yeah, so that's the basics. Thank you.
Achievements and outlook. The achievements of this phase for the development of the VR platform are the creation of the first Lego-like virtual reality build tools, the creation of a holo table that's the centerpiece of using the build tools to design buildings, the ability of multiple users to collaborate within the platform in real time worldwide, and the ability to access web content from within the virtual reality platform. The next steps for the VR platform are the further development and enhancement of the build tools, the ability of a user to create their own custom Lego packs, then upload these Lego packs and design buildings with their own Lego packs, the enhancement of the materials and the lighting within the system, the start of the development of the digitalization bridge to the real world, so we can start to scan and map an environment and then bring that environment into virtual reality. Then the ability to actually turn on that environment on the holo table, so user can now create within that scanned, mapped virtual environment. The first public release on Steam, the creation of a desktop app, as well the creation of a mobile app. On the development side of the robot system, the achievements are: we successfully created the first stage of the robotics platform for Broadcore that is needed to realize the Avabot system's vision. The realized stage of the system is the Avabot, a tailored operating system that lets a user control a robot for virtual reality, as well as a touchscreen that is connected to the robot via Wi-Fi and the internet. The Avabot system is built on top of the robot operating system. Because of the way the robot operating system is made, programs developed for one robot can be used to control other robots. As the robot operating system is a standard in industrial applications, we will be able to replace our simple servo motor robotic arm with an industrial arm in the future to realize the full capacity of the system. What are the next steps for the system? In the next development phase of the system, we will integrate ROS Sharp into our system. ROS Sharp is a bridge between ROS and Unity 3D that was developed by Siemens. This bridge will allow us to have an even greater control and access to the robot from within our Unity VR application. We will also improve the robotic arm control by integrating Movelt. Movelt is an extension of ROS, which will give us the ability to create a more intuitive arm control from virtual reality than the available one in the current system. It enables motion planning, inverse kinematics, and gives us the ability to directly interact with cameras and distance sensors. So the arm can, for example, by itself localize objects and pick them up autonomously. Another big update planned for the next phase is the upgrade of the hardware from the currently used Raspberry Pi to the NVIDIA Jetson hardware platform. NVIDIA developed an advanced computing platform for robotics and AI application that is currently 3 different units, with a 4th unit, the Savior NX, to be realized this year. A user can choose which hardware fits his need based on the pricing and needed processing power for his application. We designed the Avabot head so it can fit the NVIDIA Jetson Nano, which is the smallest member of the hardware platform. The Jetson Nano is more limited in its processing power. It's a good fit for prototyping, as it is the cheapest model of the series and is fast enough to run advanced AI algorithms. As soon as NVIDIA releases the new Jetson Savior NX, we will be able to exchange the Nano module with the new Savior model, as both of them are pin compatible. The Jetson Savior will give us the ability to connect multiple cameras to the system, so we can run advanced computer vision, and also to run even more advanced AI algorithms on the system. By upgrading to the Jetson hardware platform, we will also be able to utilize NVIDIA's new robot platform called ISIC. ISIC comes with a large tool set and integration, which makes it a huge enabler for robotics application. NVIDIA released a bridge to the robot operating system, so we will be able to run ISIC and ROS in parallel to combine the power of both systems. ISIC also has an advanced integration of AI frameworks, for example like TensorFlow and PyTorch. And it comes with pre-built AI algorithms like posture estimations, speech recognition, navigation, depth perception, and many more. So we will be able to use these pre-built AI algorithms and run them on the Avabot system to give it AI capabilities. NVIDIA also recently released a package for Unity with which a user can access data from the robot in Unity 3D, which is similar to the ROS bridge that we want to integrate in the next phase. It makes it possible to create a whole simulation environment for a robot to train one or multiple robots. In this picture, we can see an example application that has been made by NVIDIA. It is a simulation of a warehouse environment. And NVIDIA used this virtual environment to train multiple robots to fulfill tasks within the warehouse. And this next picture shows how the robot can see the virtual world. And we can see it is very close to a photorealistic world that is needed in order to use the computer vision aspect of the system. And the robot can basically run and be simulated within this environment and be trained to fulfill tasks. Integrating the existing package will give us the ability to create our own virtual environments and take a huge leap forwards towards realizing the bigger vision of the Avabot system, of creating and testing buildings and factory automatization inside the virtual world. ISIC also utilizes a web interface to access data from robots. Due to the modular nature of web interfaces, we will be able to integrate components of the interface into our existing web interface application to further enhance the robot access and control for our web user interface.